So, in the last class we were discussing about the differential amplifier as a basic building block, and we saw how it can be thought of as being a stage which has been developed as an alternative to discrete circuit common emitter amplifier configuration with all sorts of bypass capacitors and coupling capacitors being removed altogether and being replaced by transistors, and it results in a neat configuration which actually has better performance than the discrete common emitter stage in terms of being able to handle larger signal swing for the same percentage distortion and also the same gain it has, right, as that of the discrete stage. So, let us now see how this differential amplifier has certain non-idealities associated with it and how this performance of the differential amplifier can be measured in terms of its parameters. What are the parameters associated with the differential amplifier? The first one we said is the small signal parameter. And in this case, I have asked you to evaluate the signal level which is required to produce 1% distortion at the output, and you will note that it will be of the order of few VTs, right? Okay. So, it is dependent upon VT, which is 25 millivolts, okay. And therefore, if the signal level is small, where the performance of the differential amplifier can be approximated as being linear, then the input impedance of the differential amplifier for the differential mode signal is going to be how much? 2 RE into HFE plus 1, and RE being equal to 2 VT divided by I naught by 2, where I naught is the current source current and I naught by 2 will be the current quiescent current through each of the transistors T1 and T2. So, this is equal to 4 VT divided by I naught into HFE plus 1. So, this is one of the design parameters. You might be required to design this as an input stage, at which point of time you would like to know what is the input impedance of the stage. As I earlier pointed out, the input stage has the primary responsibility of taking care of input impedance. Okay. The priority that should give in terms of parameters of the differential amplifier itself differs depending upon where exactly you are using the differential amplifier. So, in this case input impedance is a very important small signal parameter. Okay. Then we have the gain of the stage, differential mode gain, is equal to, okay, is nothing but, we have seen last time, it is nothing but GM into RC. This is differential mode output to differential mode input, okay, which is strictly speaking V naught 1 minus V naught 2 by V I 1 minus V I 2 is going to be equal to minus GM into RC. This is what we have shown last time, and this is going to be equal to, again GM is V that is operating current I naught by 2 divided by VT. So, that into RC, or this is equal to minus I naught RC by 2 VT. I am writing this in terms of the operating current and other well known parameters, so that given the operating current you get quickly a picture of what the input impedance is, what the gain is straight away. Now, we also must know something about the output swing. Suppose it is not used as the input stage of an amplifier, it is used as an output stage itself, then the output swing becomes important. If it is used as an input stage of an op amp, then input swing and output swing, these are going to be very small, is going to handle signals of the order of microvolts. Even if the gain is 100, the output swing is going to be of the order of hundreds of microvolts. So, please remember that when the differential amplifier is being used as an input stage, the output swing is of no consequence. Subsequently, one might for operational reasons even operate the input stage very near saturation. There are instances, okay, where the transistor is on the verge of saturation for maybe reasons that we will explain later, okay, wherein the swing is very small. It remains in the active region even though it is on the verge of saturation. Okay. So, the swing problem as far output swing problem as far as the input stage is concerned is of no consequence, but swing problem is a serious thing only when you consider the differential amplifier coming as an output stage. Okay. So, in such a situation the swing, output swing is equal to how much? This also we had evaluated earlier. This I naught RC comes either through this or through this, at which point of time one of the transistors is off. Okay. So, that means the swing is plus minus I naught RC. As long as the transistors themselves do not go to saturation. The entire switching occurs due to current being switched from one transistor to other. Okay. Now, these are the things which we have discussed in detail in the previous classes. Yeah.
Or VCC, whichever is lower.
No, that is what I am telling. As long as the transistors are not going to saturation, it is independent of supply voltage. Okay. The supply voltage question comes into picture only when limitation occurs because the transistors are going to saturation. Is this clear? Okay. That is why you can actually design it for a given swing, okay, as far as this stage is being used as an output stage. Now, let us further discuss about other small signal properties which we have sort of postponed to this class. This particular thing, when it is having no differential mode signal, when it is having only common mode signal, both the inputs are connected together to the same voltage. This situation arises, once again I want to clearly tell when exactly it arises, in a troublesome manner, because if you do not want to bring trouble unnecessarily. When this input stage is being used without feedback, you will not unnecessarily cause common mode problem to you, right. You will always try to eliminate any problem. Where will it come without you are asking for it? It is going to be appearing in a negative feedback situation. The worst case of common mode trouble occurs in a unity gain mode of operation. Let us see this. The common mode signal situation, if this is V I, this is going to be V naught. and the entire output voltage is fed back. So, what is the common mode voltage of a unity gain amplifier? Vi itself. And you would like Vi, when this is acting as a buffer stage, to go as much as VCC itself, right, in any practical situation. That means the input common mode swing capability of an input stage which is being used in an operational amplifier is constrained to operate in this mode, as long as you are going to use it as unity gain amplifier. This problem is very severe. If you say that I will never use this amplifier in unity gain mode, where is it least severe? Where there is no common mode? What? No, open loop is a situation where there is no feedback. So, there is unnecessarily you are not going to bring in any common mode problem for yourself. Where there is an application where it automatically comes in, but comes in with less severity than this, is this you should know, because in an inverting mode of operation where one end is connected to ground, the other end is automatically at virtual ground. So, the common mode voltage input to the op amp is 0, very nearly 0. And therefore, if you have a common mode problem with any op amp, you should use it only in what stage? Inverting, safe. If you want any op amp to be chosen for being used as a buffer stage, then make sure that there is no common mode problem. And the fact I mentioned, if the stage input stage is designed such that input stage is likely to go to saturation and you are going to use it in this configuration, then the problem of what? Latch up is going to arise. Is this understood? That is where this so called negative feedback itself turns it into positive feedback because of the signal, and thereafter it refuses to come out of positive feedback situation. Right. This point is clear. So, these are clear examples where you as design engineer should know how to design an op amp given its application. Okay. Where is it going to be most likely to be used? If it is going to be a general purpose op amp which is going to be used in any mode, then you would design it for the worst case, okay? And the worst case is the maximum negative feedback situation, that is called the buffer stage. So, this situation please bear it in mind. Okay. Now, as far as output common mode swing is concerned, that is input common mode swing. That is an important criteria. We said output common mode swing is going to be negligibly small. We are not bothered about that. So, input common mode swing is concerned, what is it going to be? It is going to be governed by the amount of drop, DC drop that is occurring in RC. That is how we said we will go in for an active device or a current mirror as the load, because this potential is VCC minus I naught by 2 RC. Even when the common mode signal is present and it is varying, it is going to remain at that, and therefore, we are driving this transistor to saturation just by common mode signal, okay, even though it is not really getting affected by the differential mode at that point of time, right. Just the common mode signal alone can drive it to saturation and create the problem of latch up. That is why we said we will replace this by active device okay. This is what we introduced last time, current mirror as the load. Now, today we will see how the swing here goes almost up to VCC minus V gamma on this side, and also okay, almost to the negative supply voltage minus VEE plus V gamma, okay, plus one more V gamma, right. Up to that it can swing as far as the input common mode swing capability of the transistor stage is concerned, right. So, that means it is almost up to plus VCC on one side and minus VEE on the other side, almost. After you replace it by means of a current mirror. Now, let us see what is the consequence of this on the gain. That is, the gain that we are now going to talk about is again the differential mode gain. Does it get disturbed because of this kind of load? Please remember here that this is not the same as two equal resistors. I am putting a current mirror here. So, the current in this I and the current in this will always remain the same, always. Okay. Even when the signal comes, it should not get disturbed. So, what happens is when I apply a differential mode signal to the input, what happens? This VID divided by 2 RE, okay. This is going to be the incremental current in this emitter, right. So, the current here is going to be I naught by 2 plus VID by 2 RE, and this current is I naught by 2 minus VID by 2 RE. All of you agree with this? What will be the current in this? Very nearly same, except for alpha. Alpha times this will flow through this. Alpha is very close to 1. So, this current is going to be very nearly same as this current. What is this current? Same as this current. That means, we have a current here which is I naught by 2 minus VID by 2 RE, and this current is I naught by 2 because of the current mirror action plus VID by 2 RE. So, what happens now? Current has to come out of the output terminal into the next stage. That is what you want. Why did you use a current source as the load? Because you want the entire output current to signal current to go into the next stage. Okay. So, it is serving that purpose, and what is that current that is being injected out? VID by R. What has happened? This is with reference to ground. Okay. If you now connect a load across this, which is how much? RC, whatever it is, the output voltage will be VID by RE into RC or GM into RC. That means, you are getting back the single ended output you are taking, you are getting back the differential gain output as the single ended output. So, this is a method of converting the so called differential output into single ended output. So, using a current mirror has resulted in not only improvement in the common mode swing capability, but also has resulted in the differential output getting converted into single ended output. So, this is an important advantage of using current mirror. That means, now the output can be taken okay, with respect to one collector and ground, and you will get the same gain as previously. Is this point understood? We had noticed how replacing the two resistors by means of a current mirror has resulted in a gain which is the same as that of the earlier differential mode gain, but with reference to ground, you are now taking the output from one collector alone. Okay. Now, please remember that you are connecting the normally the next stage, which may be another differential stage. Okay. If you are taking it as a differential output, you have to connect another differential stage from here, so as to exploit the full gain. Whereas, if you have replaced it by means of a current mirror, you can take it out of only one collector. That is the high impedance point. That is the only high impedance point. The other portion, which is nothing but a diode, is a low impedance point. Okay. So, the only one high impedance point exists in the case of a current mirror, okay, that is the other collector. As far as the gain itself is concerned, it is not infinity. The current source impedance will be coming as the load impedance apart from the input impedance of the next stage. So, actually speaking, in a practical situation, the current source impedance will be replacing RC as well as the input impedance of the next stage. These two will come in parallel. Now, as far as this particular stage is concerned, we can replace this portion of the circuit by means of its dynamic impedance. The current source has a dynamic impedance, let us say RD. So, the AC picture of this stage will look like this. This is grounded. This RC may be the actual resistance, or it could be the output impedance of the current mirror as well as the input impedance of the next stage taken together. So, this is the AC picture. Now, let us consider this stage. I would like you to view this differential amplifier in slightly a different manner now. Same analysis. When the input here is VID by 2 and this is minus VID by 2, the common mode voltage is 0. That means, signal applied is only differential mode. This is a perfectly symmetric circuit, and therefore, the potential at this point, which is the common point in the symmetry, is going to be 0 at all times. So, because of symmetry, I can say that this point is going to be at all times at 0 potential, in which case I can as well say that this is grounded. Only if it is purely differential mode, okay? Not if it is having common mode as well as differential mode coming. Is this point understood? That means, whatever increase in potential that arises out of the incremental current injected here will be removed by the current flowing in the opposite direction through the same impedance. So, essentially mutual cancellation occurs, and therefore, potential does not change. That means, incremental picture I can ground this. So, this is an important advice to you, that any differential stage for analysis purpose, okay, for differential mode analysis, you can simplify it considerably by simply grounding this point for differential mode analysis. In which case, you can see that the gain is going to be RC divided by 2, that is RC divided by RE, okay, here. RE itself is going to be governed by I naught by 2, okay. RC by RE here and RC by RE here, okay. The phase shift is because of the assumed shifting of this here, okay. This will be out of phase with this by 180 degree, that is the signal we have assumed, okay. So, this is the analysis that you can adopt for differential mode. Anyway, that is nothing new about it. We have already learnt about the differential mode gain. Now, let us see for the common mode what happens. when the signal is only common mode, VC, VIC, VIC, it is still symmetric. What happens? The signal here is going to be very nearly VIC, except for a small drop in RE, small RE. So, this potential is going to almost nearly follow this potential of VIC. That means, the incremental change here is going to be very nearly equal to VIC divided by RD. Except for the small drop that I have ignored through RE, okay? Which means I can consider that it is VIC by 2 RD and VIC by 2 RD, okay? Two current sources, okay, flowing that way, VIC by 2 RD, VIC by 2 RD, summing up to VIC by RD. That means, actually speaking, you can now see that which is VIC by RD. Now, there is no current going to flow through this link at any time, because the potentials will remain the same at all times. So, I can as well break it open. Is this point clear? So, that means, for the common mode operation, I can have the circuit split up as what is VIC by 2 RD equivalent to VIC is the drop across the current source and VIC by 2 RD is the current through it. That means, it is equivalent to a resistance of 2 RD, and this also is a resistance of 2 RD. So, for common mode signal, now let us see what happens. What is the input impedance for common mode? Okay, input impedance R 2 RD plus RE. So, 2 RD plus RE, which can be ignored anyway, okay, into HFE plus 1. This is also mentioned by the manufacturer. Okay. For any differential stage, he will also give input impedance for differential mode, okay, and input impedance for common mode. This has to be very, very high. That is very high, particularly by using, okay, a current source there or sink. We are simulating very high impedance for it. Then, what is the gain? This is the current. What is the current? Emitter current? VID divided by 2 RD plus RE, that is the incremental emitter current, and what is the incremental output voltage now? Into RC. So, that single ended common mode gain is going to be nothing but RC divided by 2 RD, if you ignore this, right, because that is very small, RC divided by 2 RD, right. So, this is nothing but the common mode output voltage. Okay. So, common mode gain is going to be equal to RC divided by 2 RD. Is it clearly understood? Now, if you take the differential output, this output voltage will be in phase with this output voltage for common mode signal. So, the differential output will be still 0, but for a measure of common mode output voltage, therefore, it is advisable to use single ended output in the case of a differential amplifier. So, if this outputs themselves are very small, if VOC itself is very small compared to the differential output due to differential mode signal, then making this equal and getting it cancelled is an easy affair. So, a measure of what? How good the differential amplifier is determined by finding out the ratio between what? The differential mode gain and the common mode gain for single ended output.
What will happen if you put a terminal there? Is it going to be zero differential output even in the case of a common mode?
Yes, the entire differential mode of operation has come about not due to output at all. Please have that very clearly in mind. It is only due to input arrangement of having a current source here, that is responsible for the differential mode. Right? How you are connecting what at the output is of no consequence. That is what I am trying to make clear to you. Okay? The rejection property for the differential amplifier has come about because of using a current source at the input point of the stage. Okay. What you connected, because you can see that both common mode gain as well as differential mode gain will be dependent upon what is differential mode gain? RC divided by 2 RE. Okay. Is this clear? RC divided by 2 RE is the differential mode gain. So, it will get cancelled. If you take the ratio, common mode rejection ratio is nothing but what? AD by AC, and it is independent of what I am connecting at the collector, because the rejection property is due to the current source that I am feeding, current sink that I am feeding at the common point of emitters. Okay. So, RC get cancelled, it is purely a property which is dependent upon RD and RE. So, let us see RD divided by RE, and what is RE again? RD divided by VT divided by I naught by 2. Now, we have quantified every one of the parameters, small signal parameters associated with the differential amplifier in terms of the load resistances as well as operating current, including its swing. Okay. So, now you can design depending upon where is it going to be used. Is it going to be used as input stage of an op amp, or is it going to be used in a video amplifier where the stage itself has the responsibility of input and output, okay? Because there the output swing also is going to count. Okay? The signal may have been already amplified sufficiently large. Okay? So, it may be used as a power driver stage, the differential amplifier. So, depending upon that, you have to decide what is the parameter that should become important. Obviously, in the input stage, the important parameters are input impedance, that is differential mode, input impedance common mode, okay. That itself will take care of common mode rejection ratio. If you take care of input impedance, that itself will take care of common mode rejection ratio, and gain is of no consequence. Okay, you can forget about it, because CMRR is independent of what you are connecting at load. Okay. So, this is what you should consider when it is being used as an input stage. Okay. As far as last signal property is concerned, once again common mode swing at the input, okay, differential mode swing at the output, which is nothing but I naught into RC, and the relationship between VID and V naught D, which is nothing but tan hyperbolic function. These are the things that you have to remember in the case of any differential amplifier. Clear? The same thing is applicable when the differential amplifier is MOS based or JFET based, okay, except that the relationship is not hyperbolic, it is square law, right, if you use a resistive load. But again, if you use a MOSFET itself as the load, then again it becomes actually linear over a certain range. Okay. So, I would like you to do the same kind of analysis for MOSFET differential amplifier using resistance as the load, okay, and see what kind of relationship occurs between output V naught D and input V I D. Rest of the discussions regarding what is that common mode rejection ratio etc. remain the same. Okay. So far we were discussing about small signal properties as well as large signal properties of the basic differential amplifier. Now, we will go to the secondary properties of the differential amplifier, which also become important when we use this in particularly low frequency or DC amplifier stages, the so called video amplifier stages also. Let us see what these are. What we are now going to discuss will be primarily to do with offset voltages, okay, output offset voltages. Any amplifier, okay, the output is a function of input, that is generally, okay, the property of any amplifier, some general function. We would like this function to be normally any general amplifier, right, it will be a factor independent of V I, okay, that is a voltage, let us say, that voltage is called offset voltage. So, in any amplifier, in whatever form of biasing you use, it will have this kind of property that it is function of V I, and the factor independent of V I is always called the offset voltage plus A times V I, okay, linear dependence, and what non V I squared factor, V I cubed factor, and all this. These are the non-linear, okay, output due to non-linearity, right, V I squared etc., V I cubed etc. So, we are biasing the op amp or the differential amplifier in such a manner that these terms are made very small for a given V I. That is why biasing becomes important. Okay. Apart from that, we would like to make this offset also go to 0. Why, you might ask? Because the delta V naught by delta time, right, is going to be delta V offset by delta T. Obviously, it will also depend upon delta V I by delta T etc. Right. This has been made 0. Okay. We are discussing the situation where these two exist. In such a situation, delta V naught by delta T is called what? What is it called? This is the drift. That is, the output is going to drift because of what? Even if the input is 0, even if the input is 0, right, even if when input is 0, okay, the output drifts because V offset is changing with respect to time. And that itself is going to get mixed up because we cannot make a distinction between this which is changing with respect to time, okay, which we want to sense, and this, these are mixed up. That is particularly so if we are not able to isolate this. Drift is a very low frequency phenomenon, and therefore, if our signal itself is a low frequency thing, we are unable to separate this. If the signal is a high frequency signal, then we can separate out the drift component by using a capacitor, right, just a capacitor, decoupling capacitor. But when the signal is low frequency, particularly in the case of video amplifier or biomedical amplifiers, okay, that it becomes important that I should make this offset as small as possible. That is the reason offset is made small. What is causing you trouble is not the offset itself. What is causing you trouble is dependence of offset voltage on temperature, time. Okay. It depends upon temperature, it depends upon operating voltage, etc., and therefore, with respect to time it keeps drifting, and that is causing us problem. Okay. So, this has to be eliminated, particularly in situations where you are designing high gain amplifiers. This might drift the output quiescent point to such an extent that the operating point goes to nonlinear regions, and linearity itself or the gain itself gets reduced. This also is a danger. So, therefore, offset has to be reduced considerably. So, how do we therefore measure this offset? How to therefore come out with the design parameter, so that we can say this differential amplifier or the op amp is better than another differential amplifier or op amp. That measure is another important parameter associated with op amps or differential amplifiers. So, we will come out with what is called as input offset. Because input offset is the one which is causing major problem, because input offset voltage is going to be amplified by the entire gain and is going to appear as output offset, and therefore, the danger is the input offset itself. Let us see, right. The input offset, if it is common mode, it is automatically rejected, right. That is the purpose of using differential amplifier. Okay. Can it become differential mode? It is not in our hand. Let us therefore see, if it becomes differential, then the danger exists, right. So, what does it mean? Now, you have understood that input offset can result due to the difference in the two voltages. What is this? If the input is 0, these VBEs are the same. If these VBEs are the same, what will be the emitter current here? IE1 and IE2. IE1, okay, is equal to IE0 exponent VBE by V2. Is this clear? And IE2 is going to be equal to IE0 exponent VBE by V2. These are going to be same. Right. So, even if VBE changes with respect to temperature, this will remain the same, no problem. This is what is called common mode problem. Okay. VBE changes with respect to temperature, but these currents will remain the same. What will be the value? Is going to be I0 by 2, right, because IE1 is equal to IE2 and it is going to be equal to I0 by 2 by Kirchhoff's law, and therefore, output offset is going to be 0. But when will output offset come into picture? When IE1 is different from IE2. That can only arise when IE01 is different from IE0, that the two transistors are not exactly matched. If the two transistors are not exactly matched, okay, IE1 and IE2 for the same VBEs will be different. Then there is going to be an output offset voltage because of this. So, what is it that causes output offset voltage? the difference in the two transistors, and that is resulting in an equivalent differential mode signal. And what is that differential mode signal? That we can say the input offset therefore is defined as that voltage that I have to apply at the input in order to make IE1 equal to IE2. The input offset therefore is that voltage that I have to apply at the input, okay, to cause IE1 to be equal to IE2. That will be then equal to I naught by 2. What is the input voltage that I have to apply? As what? Delta VB, delta VI at the input in order to cause IE1 to be equal to IE2 artificially. That is what is called as input offset. How do you know that? You can now find out if IE1 is equal to IE2 I have made, then that is equal to I naught by 2. Then I take the ratio of this, what do you get? VBE1 has got to be different from VBE2. Okay. That means VBE1 minus VBE2 is going to be delta VI in that loop. Delta VI is nothing but VBE1, okay, minus VBE2, okay, VBE1 minus VBE2, and that is nothing but how much? Take the ratio, okay, VT log IE naught 2 by IE naught 1. Is this point clear? Take the ratio here, the currents are equal, so this becomes 1, IE naught 2 by IE naught 1 is equal to exponent VBE1 minus VBE2 by VT, and therefore it is VT log. So this is defined as by the manufacturer, this is defined as the input offset, because only manufacturer has to tell you what it is. It depends upon the transistor mismatch. Typically for the technology that exists today, okay, for the bipolar transistor, this is ranging between 1 to 2 millivolt, okay, 1 to 2 millivolts. Is this clear? So this is coming because IE naught 2 is not exactly equal to IE naught 1. This is very nearly equal to 1. That is why this logarithmic factor is going to be a small factor, and VT itself is 25 millivolts. Okay. So some factor of about 1/10 will come out of it, and therefore you get 1 to 2 millivolts as the natural uncertainty about this. Right. If we use one pair, this is the input offset. If we use two pairs, each of the pairs will result in what? 1 to 2 millivolts of uncertainty. So uncertainty will keep on multiplying with the number of pairs. So please remember this in your design, that for whatever reason, if you increase more pairs, what is these are called? Darling pairs or Darlington pairs. Right? Why do you use Darlington pairs? You want to improve the input impedance of the input stage, then you might go for Darlington pairs. So when the input impedance is increased, automatically you are sacrificing input offset. This is the practical situation that exists. In the case of a MOSFET, for example, differential amplifier, what is the uncertainty due to? Here VBE is of the order of 0.6 or so, right, and it is 0.6 for the same current, that means 0.6 here, 0.6 here. It is uncertainty in 0.5 to 0.6, whereas in the case of MOSFET it may be some 1 to 2 volts. Okay. So the uncertainty also, magnitude also increases, it in fact increases by an order of magnitude. It will be of the order of 10 to 20 millivolts. Okay. That is uncertainty in VGS. Okay. For obtaining the same current, okay, the uncertainty in VGS is going to be one order of magnitude higher than in the case of a bipolar transistor, that is for the MOSFETs. So, please remember, if it is input offset that is the choice for the input stage, then MOSFETs are out of question as input stage. You would rather prefer bipolar stage, but MOSFET has given you the highest input impedance that can be given, right. So, always remember that input impedance, if you are concerned about, you have to sacrifice input offset. This is the primary sort of idea behind selecting input stage. Okay. If you want low input offset, go for low input impedance, that is all. Okay. You cannot help it. So, VB even means this is what is called as input offset. Apart from that input offset, we have other offset problems also. Why? This particular stage may not be just grounded. You are connecting an input source here, okay, normally, and when the signal of the source itself is 0, that impedance RS is always coming into picture. So, since there is a base current flowing in this, okay, which is IB1, this base current IB1 into RS itself will act as an offset voltage. This is called bias current offset. That is coming into picture only when you are having source which is having high source impedance connected to the input. One way to tackle that easily is to connect another RS. That solves your problem partially, because unfortunately even if the transistors are very well matched, the betas need not be exactly same, and IB1 and IB2 may be different. So, even if you put equal resistors, right, there may be therefore a resultant offset voltage which is due to IB1 minus IB2 being not equal to 0 for the same emitter current. Okay. This is defined as current bias current offset. Okay. This again is not present in the case of MOSFET. So, in the bipolar stage you have, apart from delta VBE offset, this is called delta VBE offset, you have bias current offset also. Okay. This as worst case situations, that means you have to add these voltages always. Okay. So, one way to tackle this in a very crude manner is always connect from the input to ground or virtual ground an effective DC resistance which is, okay, equal to the source resistance, okay, if it is not a feedback stage. Otherwise, the principle is from plus and minus both terminals to ground, you must connect equal valued DC resistances for count bias current offset. These have to be done particularly for low frequency design, where the drift is a major problem. Okay. So, pardon? If it is a DC, it is not a problem. This is going to turn itself into a drift problem, because IB beta is heavily dependent upon temperature, okay, and therefore, that in turn changes with temperature, that in turn causes, okay, problem for us to isolate it from the signal. And if it is a DC, actually if it is DC, problem for us, right. You know completely about the signal, right. What is noise is time varying signal. Okay. So, we will stop here for today and discuss more about application oriented differential amplifiers in the next class. That is, how designs have to be slightly different when we design this differential amplifier for high frequency application, etc., etc. So, specific differential amplifiers, okay, to be used in will be discussed from next class onwards.